Okay, so in this video, we're going to go back to section 4.5. We left off in section 4.7, which was on optimization. We're going to go back to 4.5, which is on curve sketching, and that is going to use all the tools that we've developed all about the derivative to tell us things about geometric properties of the function. So we're just going to look at one more example in that section. All right, so hopefully you can see this. So this is on, we're going back to 4.5, and this is on curve sketching. And we're going to look at example 3. So for example 3, we're going to sketch. And by sketch, we always mean just a rough plot. So sketch the graph of f of x is equal to x times e to the x. And so as always, by a sketch, we just mean a rough plot. It doesn't have to be precise or extremely detailed or even up to scale. It just needs to just display the general geometric properties of the function, where it's increasing, decreasing, where it has relative or local extrema, local minimum or maximum, and inflection points, which are the points where the concavity of the function changes. So the first step is to find out where this function is defined, because those will be the only places we can plot or sketch this function. But in this case, the domain is pretty easy. The domain is just every real number. There are no restrictions. X is the function x is defined everywhere, and the function e to the x is defined everywhere. So their product is defined everywhere. But what about intercepts? So those aren't difficult to find either. So the x-intercept is just the value of x you plug into the function that makes the function 0. So x is equal to 0 is the x-intercept. So when you plug in 0 to the function, you get 0. When you plug 0 in for x, you get 0. And then the y-intercept is you find that by setting the function equal to 0 and then solving for x. So in that case, we're going to see that y equals 0 is the y-intercept. So I guess you could just say that the point 0, 0 is the x and y-intercept. Oops. So the next question is, does this function have any symmetry? So for example, is it even or odd? And the answer is no, neither. It's not. It doesn't have either. So it has no symmetry. To see that, I guess you could just plug in numbers. So let's recall even and odd first of all. So even means, so if the function is even, it means that f of negative x is equal to f of x. And that has to hold for every x. Oops. Every x in the domain. And actually for these functions for functions to be even or odd, the domain has to be symmetric about 0. Otherwise this equation doesn't make sense. You need that if x is in the domain, then negative x is in the domain. So in this case, we do have our domain is symmetric because it's the whole real line. It is symmetric about the origin. So it makes sense to ask whether it's even or odd. But you can see that it's not. So you can say if it were, then for example, this equation would hold. Just take any two numbers to see if it's even or odd. And that implies, and what you're going to end up is, so we're going to assume by contradiction that this function is even. And then we're going to derive some absurd or contradictory statement. And then that'll allow us to conclude that the function can't possibly be even. So we're going to imagine it is even. And then if it were even, then we have to have in particular that this equation holds. But this is the same thing as negative negative 1 times e to the negative 1, which is equal to 1 times e to the 1. And that simplifies as negative 1 to, it just simplifies to negative e to the negative 1 is equal to negative 1. And you can also write this as, so now you multiply both sides by e to the 1 first power. So they'll give you e to the second power is equal to negative 1. But e to the x is always positive. So I use this symbol, this kind of lightning bolt symbol for contradiction. So this is the contradiction. So implies that f can't be even. So this is the contradictory statement that we wanted to derive. That the exponential function, the real exponential function, is always positive. It's never 0, and it's neither 0 or negative ever for any value of x. So this implies that it can't possibly be even. And so odd, let's look at the odd case. Let's look at odd symmetry. It's also not going to be odd either. But what does that mean? So odd means that f of negative x is equal to negative f of x for every x in the domain of f. And again, for a function to be odd, first of all, the minimal requirement is that the domain has to be symmetric about the origin. So you need symmetry about the origin of your domain for even and odd function. And again, our domain is the whole real line, so it is symmetric about the origin, so it makes sense to ask whether this function's odd. But it's going to turn out that it's not. So again, you just do a proof by contradiction. If f were odd, then we would have to have, for example, just use the same value of x, just negative 1. We would have to have this. And this would give us, let's see, negative 1 times e to the negative 1, which is equal to negative e to the 1. So we're almost basically we're actually, something's not right, actually. Let's see. If you simplify this, then oh, I see. So for this, so now the contradiction is going to be different. So if you assume that it's odd, then you have to have that this equation holds in particular, but this equation is equivalent to this one right here. You're just plugging in negative 1 for x into the function, and then plugging 1 and then negating it right here. And it gives you this equation right here. And you can cancel the negatives on both sides. And then again, you can multiply, as we did up here, both sides by e to the first power, and it gives you that. But we know that e to the 0 is 1, and e to the x is injective. It's 1-to-1. It's a 1-to-1 function, meaning that if you have two distinct points, they should have this distinct output. So since it's injective, this implies that 0 equals 2, and that's obviously absurd. This is a contradiction. 0 is not equal to 2. So it implies that f is not odd. I guess you don't have, for an exam, you don't have to be this detailed. If it's just sort of clear to you that the function is even or odd, then you can just state that. Unless I say justify, unless the problem says, is the function even or odd? And then I ask you to justify it, you'll have to go through something like this. This sort of reasoning, you have to demonstrate that the function is even or odd or neither. But if I don't ask you to justify it and it's clear to you, you can just state it. But if it's not clear to you, it's good to go through these steps to show you why this function, a given function, is even or odd or neither. So just how the logic works again is that this is what it means to be, first of all, odd. And if f were odd, so we're assuming by contradiction, suppose that f is an odd function, then you have to have that this equation holds in particular. And this equation is equivalent to this one. And then it simplifies to this one. So it says e to the second power is equal to 1. But we know that e to the 0th power is 1. And e to the x is injective. So what we have is that, what this says is that e to the 0 is equal to e to the second power. And so that implies that 0 has to be equal to 2, but that's ridiculous. That can't happen. 0 is not equal to 2, so f can't be odd. So I just maybe put in parentheses here. For this particular case, EDX being injective, this is what I mean by injectivity and how I'm using it. EDX being injective means that if e to the x equals e to the y, that implies that x equals y. That's what injectivity means in this special case. But it's pretty clear what it means more generally. So it can't be odd either. So it has no symmetry. What about asymptotes? So first of all, we want to look at horizontal asymptotes. Well, first of all, actually, I should just rule out vertical asymptotes. There are no vertical asymptotes. So there are no vertical asymptotes because there are no points where f of x is not defined. This function, f of x is equal to e to the x, is defined everywhere. And vertical asymptotes can really only happen at points where your function is not defined. So for example, if you have a function that's defined as some sort of fraction, the function in the denominator, the roots of it will give you rise to vertical asymptotes, but we don't have denominators or anything like that. There are just no points. And for example, we don't have the natural log of x. So we know that is not defined at the origin. So, if you look at natural log of x, it looks like this. So this is natural log of x. It has a vertical asymptote at the line y equals 0, x equals 0. So that's the y-axis, because ln x is not defined at x equals 0. But we don't have any such points. The function is defined everywhere. So there are going to be no vertical asymptotes. So we just need to think about horizontal asymptotes. So how about horizontal asymptotes? Does it have any? Well, remember, to find the horizontal asymptotes, we need to compute two limits. The limit of the function as x goes to infinity and negative infinity. Now, as it's clear that, clearly the limit of f of x, which is the same thing as the limit as the limit of f of x as x goes to infinity, which is the same thing as the limit of x times e to the x, because this is by definition f of x. These limits are the same. And this is obviously going to be infinity. This is the part that's clear, that this is infinity, because x and e to the x go to both, each individually go to infinity as x go to infinity. So their product was going to go to infinity. But what about the limit as x goes to negative infinity? Well, as x goes to negative infinity, obviously x goes to negative infinity, so that's the first thing in the product. But e to the x goes to 0, so implies that we have that x e to the x, I guess in quotation marks because this isn't precise, but I'm just illustrating to you that we're going to have an indeterminate product. So we get negative infinity times 0, so that we get indeterminate product, which means we can write this, somehow we can use L'Hopital's rule by writing our function as some sort of fraction and get something like maybe 0 over 0 or infinity over infinity. So like at this point we need to use L'Hopital's rule. So just spell it all out. To determine the limit as x goes to infinity, negative infinity of x to the times e to the x. So let's write this on a new line. So how we're going to do that is by flipping e to the x into the denominator. So we're gonna, this limit is equivalent to this limit. So maybe take a few seconds to convince yourself that this thing equals this thing. So now if you just naively take the limit, then as x goes to infinity, negative infinity, the numerator goes to negative infinity. And as x goes to as x goes to as x goes to negative infinity, the numerator goes to negative infinity. And as x goes to negative infinity, e to the x goes to positive infinity. So actually what we need to do is, so we get negative infinity over infinity, so we just need to throw some negatives in here. So now we get infinity over infinity. And I didn't change the expression at all because this negative cancels with this to give me the original limit. And so at this point, we can use L'Hopital's rule. So, which says that you just because our functions are nice enough and we get an indeterminate form, we just to compute this limit right here, we just differentiate the numerator and the denominator separately. So we get 1 over, when you differentiate this, you use the chain rule, so you get the derivative of negative x becomes just 1, and then that cancels this negative here. And then the derivative of e to the x is just e to the x. So this is just chain rule. We have this negative still. And then at this point, we can flip this back in the numerator. And as x goes to negative infinity, e to the x is going to go to 0. And just so we're clear as to why that happens, let's draw the graph of e to the x. E to the x, from recall, looks like this. Something like that. So as x marches to a negative infinity, the function is just going towards 0. So this limit is going to be negative 1 times 0, which is just 0. So what this tells us is that what this tells us is that the line y equals 0 is a horizontal asymptote. Horizontal asymptote for the function f of x, which is given by this, and that's as x goes to negative infinity. So it approaches this line y is equal to 0 as x goes to negative infinity. So now we just need to determine increasing and decreasing, and then concavity. So let's do increasing and decreasing first. So in order to find where it's increasing or decreasing, we need to take the first derivative. So the first derivative tells us, so to compute the first derivative, we need to use the product rule on it, because we have x times e to the x. We have a product, so we have a product of two functions of x. So the product rule says that you differentiate the first function, so derivative of x is just 1, times the second function, plus the first function times the derivative of the second function, e to the x, and that's just e to the x. And we can factor it like this. So now e to the x, as I noted above in our proof that the function is not an odd function, this is positive for all x for every x in the real numbers, the set of real numbers. Remember that just means this e symbol just means in. So for every x in the real numbers. So what that says is that what this says is that the sign, let me say it this way. The sign of f prime is determined by the factor x plus 1, because a product of two numbers is, say, positive if and only if the two factors have the same sign, or it's negative if and only if those two factors have different signs. So we have two factors. We have the first factor is x plus 1, and then the second factor in this product is e to the x. But e to the x is always positive, so we can just ignore e to the x and just determine the sign of f prime of x from x plus 1. So we can see that f of x is positive if x plus 1 is greater than x plus 1 is greater than 0. So what that says is that f increasing, of course, this is equivalent to saying x is strictly greater than negative 1. So f is increasing on negative 1 to infinity. And then we can see that, oops. And then the derivative is negative if or whenever x plus 1 is strictly less than 0, which is to say that x is strictly less than negative 1. So that for the first derivative test, that tells us that f is decreasing on the interval negative infinity to negative 1. And we have a critical number. Recall that a critical number is a point where the derivative is either not defined or is 0. So we don't have the derivative is defined everywhere, so we don't have to worry about that. But we do have a point where it is 0, and that's at negative 1. So x equals negative 1 is a critical point. And because the function goes from, sorry, let me see, am I messing something up? Just making sure. So yeah, so it's increasing on this interval and decreasing on this interval right here. So what that means is this critical point. So not only is x equal in a critical point, but it corresponds to a local minimum. Oops. At the critical point. And if you plug this in, the book gives you a decimal approximation, which will sort of help, I guess. If you plug in -1 to the function, you get negative e to the -1, and that is approximately negative 0.37. Turns out that this local minimum is actually an absolute minimum as well, but we don't really need to know that in order to graph the function. So we have that where it's increasing, decreasing, we have the critical point, and because it goes from increasing to decreasing, sorry, I'm sorry, I get this backwards. It goes from decreasing to increasing. So we're going from decreasing to increasing. That implies that this critical point corresponds to a local minimum. And so now the last thing we need is concavity. So in order to find that, we need to take the second derivative. So let's just write down the first derivative first. So the first derivative is given by this. So that implies that f double prime, which is just the derivative of the first derivative, is given by, well, the following. I'm going to write it down in a second, but just remember we have a product of two functions of x, so we need to use the product rule again. So the product rule says you take the derivative of the first function, which is just 1. So the derivative of x plus 1 is just 1, times the second function plus the first function times the second function, the derivative of the second function, but the second function is just e to the x, so it doesn't change anything. And now you factor out e to the x, and what you get is 1 plus x plus 1 e to the x. And that simplifies to this, and you actually might see a pattern for the derivatives. So just to point this out as an aside, you have, this is the first derivative, this is the second derivative, so first, second, and at this point it gets annoying to just write primes all the time, so then we just write, we use this notation to write third derivative, and then this is fourth derivative, and you can just keep going, etc. So what we have is for the first derivative, that corresponds to f of 0, 0 meaning you don't take the derivative at all. You just get the original function. Then you have, this is alternative notation for the derivative. This is going to be helpful later on, this notation. It depends. I don't remember if we talk about Taylor series in this class, but definitely if you go on to Calc 2, this notation is going to come up because it's just easier to deal with than writing. If you want like the millionth derivative, you don't want to have to write out a million primes or a million apostrophes or whatever. It's an apostrophe, but mathematicians just call it prime notation. So this is the 0th derivative. This is, you just don't take the derivative at all. This is the first, so the 0th derivative. So sorry, I'm just getting off on a side because I want to introduce this notation and then write something down for you, because there's a pattern that's emerging as you take derivatives of this function. So this is the 0th derivative, meaning that you don't take the derivative at all. This is the first. This is the second. And then you've got, this is the third. And then it just keeps going on. fourth, fifth. And so if you continue to take derivatives of this function, we only need the second derivative. We don't need to go any further. But when you go into Calc 2, you're going to do this thing called Taylor series, and you're going to need to calculate higher derivatives. And you can compute what's called the Taylor series of functions, because continuous functions are, it turns out that all continuous functions can be approximated by polynomials in a sense. They can be, in other words, every continuous function is actually just a polynomial with infinitely many terms. And to write out the Taylor series, or the power series is another word for it, of a continuous function, you need to compute higher derivatives. So if you continue to take higher derivatives, I think what you'll find is that the nth derivative, so this is nth derivative, so this is kind of going down a rabbit hole, but it's important to mention nth derivative is going to actually just be given by x. You can see, so the first derivative we had a 1, the second derivative we have a 2, so the nth derivative would just be given by this. And there's this method of proof. You can just, I will just write a name down, but I won't go through the proof obviously, because this is just an aside. You can prove this, and you can look up what this means. Prove this by what's called induction, or mathematical induction. So if you want to look up on your own to see what that's about, you can. So look up mathematical induction, and you use that to prove, you can use that to prove that this pattern is actually correct. But anyways, let's get back to concavity. I just wanted to point that out. So we just found that the second derivative is x plus 2 to the e to the x. So again, x plus 2 determines sign. It determines this factor that you, you're multiplying e to the x to determines the sign of the derivative, in this case the second derivative. So we can see that f double prime is, let's start with negative. Negative when x is less than -2. So this corresponds to concave, I think this corresponds to concave, yes, up. When the derivative is negative, this corresponds to concave up. It'll be concave up on the interval -infinity to -2. And then we have, it's positive when x is bigger than -2. And this corresponds to concave down on the interval -2 to infinity. And then at -2 is an inflection point. This is a point where the concavity changes. So at this point, we can put everything together and get plot this. So let's do that. So so let's see. All right. So first of all, I don't know if this will work. So the x-axis is an asymptote as x goes out to infinity. And then we know we have so first of all, let's write down our intercepts. So we have an intercept here. It goes through the origin. And then we have a local maximum, or sorry, a local minimum, say about, sorry, it's hard to draw a reasonable graph using this pen, or even in person. I suck at drawing them in person also. So we have a local minimum at the point, this point here. And then this number right here is negative 1 over e is approximately negative 0.37. So 2 might be like, say, over here, negative 2, I should say. So this is the minimum, and then this is the change in inflection and in inflection. So what we have is that let's see, this is negative 1, this is negative 2. This is a little confusing, actually. Let me get rid of this. So we have a minimum at negative 1, a local minimum, and we have an inflection point at negative 2. So that's where the concavity changes. And then right here we have, this is where the minimum happens. It's at negative 1 over e, which, as I said above, is approximately negative 0.37. And then we have this x-intercept here. And as x goes out to infinity, it gets arbitrarily close to the x-axis. So we'll start out like this, and it has to like be bumped upward because it's concave up. So this is gonna be hard. So I'm just gonna draw it and then explain why the features after I draw it. So it kind of goes, this is hard. So it kind of goes like this, and no, it doesn't go like that. And then it changes concavity here. So it's kind of bumped up here, and then it changes concavity here. And then it goes down to a minimum. Now, so from negative 2 to infinity, it's concave up. So it's kind of curved up. And then from negative 2 to positive infinity, it's going to be concave down. So it's going to be curved down. And then it achieves a minimum here. So it's decreasing here, and then it starts increasing. And we're still concave up. Or sorry, this is, this is concave up, and at this point, and then it goes up like this, not like that. Something like that. So that's my best attempt at plotting this function based on this information. So here it's concave. Here it is concave down. Here it's concave up. We have this minimum here, this intercept, and then this is the asymptote, the x-axis. All right, so that's all I want to do for 4.5. So I'm just stops for a second, and then I'll move on to 4.7. All right, so we're going to move on to section 4.7, which is on optimization. And as I was looking through the book, I realized that I didn't quite finish example 3. So we're going to do example 3 and then example 5, and then that will be the end. And then when we meet on Friday, we'll look at the last section in chapter 4, which is 4.9 on antiderivatives. And then the rest of the, probably on Monday, we'll maybe look at some new material. And then Wednesday, we'll review for the exam that's going to be on Friday. So let me share my screen. And let's see, so here's example 3. So the example is find the point on, let me see. Sorry, so if example 3 is find the point on the parabola that's closest to the point 1, 4. And so here's a sketch of what's going on over here. This is figure 6, which comes from the book. So here's the parabola in red. Here's just a generic point xy on the parabola. And then there's the point 1, 4 in the plane. So first of all, it's clear that the closest point has to be on the part of the parabola that's in the first quadrant. but it'll turn out that that's what we'll derive, we'll deduce that that point is in the first quadrant. So first we need to describe the distance between a given point on this parabola and 1,4. So we need an equation to give us a way of measuring the distance between these 2 points. So something like that. It's supposed to be a straight line, but it isn't. So we can use the Pythagorean theorem, or the distance formula. So we can say that the distance from 1,4 to x and y, and x, y is on the parabola, is given by the following. So it's x minus 1 squared plus y minus 4 squared. But xy is on the parabola, so it satisfies the point xy satisfies the equation. Oops. Suddenly forgetting how to spell this word. Oh yeah, there we go. It satisfies y squared is equal to 2x, and you can solve for x to get this. So we can write d, the distance d, solely in terms of x. So if we do that, we get this. Something's not right. The focus. I'm sorry. We solve for x, so we're going to write the distance between these 2 points solely in terms of y. So I had this x here, and I just plugged in y squared over 2 into it for it. So it turns out so really this is d is a function of x and y, strictly speaking. So we have a function d of xy. So it turns out that of the point xy, and so what we want to do is we want to find x and y that minimizes this function right here. That's what we want to do. I'm sorry, I'm a little foggy at the moment. So it turns out that this point minimizes dxy, so the distance between x, y, if and only if it minimizes this distance squared. And that's helpful because that will allow us to get rid of the square root. So dx, so dxy squared is just 1/2 y squared minus 1. So I'm not actually writing x anymore, but it is still implicitly a function of x. So it's this plus y minus 4 squared. And we're going to call this f of y. So, really what we want to do is we want to find y, some real number y, minimizing f of y. And so how do we do that? Well, we have to do derivatives. We have to find the derivative and then determine critical points, and then from there determine whether it corresponds to a minimum or a maximum. Because for all we know, maybe there is no minimum. I mean, just looking at the graph, you can tell that, yeah, sure, there should be some minimum, but you have to prove that, and that's precisely what we're going to do. We're going to prove that. So we're going to take the derivative. So we're differentiate each piece using the chain rule. So we take the derivative of the first thing. So we have to bring down the power, take the derivative of the inside function, which is, so the -1 goes away, but then the derivative of y squared is 2y squared, and then the 1/2 cancels the 2 to just give me 2. And then we multiply by the inside function. And we have to decrease the power by 1. And now we take the derivative of the second piece, and the chain rule says you bring down the power, and multiply by the derivative of the inside function, but the derivative of y minus 4 with respect to y is just 1. And then you multiply by the inside function, y minus 4, but you reduce the power by 1. And then we can simplify a little bit. So we can distribute this through to get, well, these 2's cancel out, so you get y cubed. And then minus 2y plus 2y minus 8. And then the middle terms cancel. And then it's clear that y is equal to 2 is a critical point. This is a point. So first of all, the derivative is defined everywhere. So we're not going to get critical points from points where the derivative is not defined. So we can only get a critical point from a point where the derivative is 0. So that happens when y is equal to 0. So this is we have a critical point at y equals 0. So now we just need to determine whether or not this is in fact a minimum or maximum. It's going to turn out that this is a minimum, just because geometrically it's clear that there has to be some point where the distance is a minimum, and point on the parabola where the distance is a minimum. Obviously there's no point where the distance is a maximum, because you can take this point and it can slide along the parabola out to infinity, and that distance will just continue to grow. So this better, in other words, this better be a point corresponding to a minimum. So we can say when, I guess the easiest, let's see. Yeah, so at this point you could just say that, or we could determine where the derivative is positive or negative. Now they just say it's obvious that this is a minimum, but I'm not going to take it as obvious. So let's see if this second derivative test works. Remember what the second derivative test tells you. So it can tell you whether a point is a minimum or maximum. So we'll take the second derivative, that will give us 3y squared, and then we'll plug in y is equal to 2. Times 2 squared. So that's 4 times 3 is 12 positive. So the second derivative test says, so second derivative test that at y is equal to 2 corresponds to a minimum. This critical point corresponds to a minimum. So you could determine that this corresponds to a minimum by looking at where by looking at where the function is increasing or decreasing by looking at the sign of the derivative. That's fine, but rather than do that, it's easier just to use the second derivative. Sorry, this is it should say second derivative test. So it's easier just to use the second derivative test at this point. So this corresponds to a minimum, and now we can just work out what the so we know the y coordinate, so now we can get the x coordinate. So x, remember, recall x comma y, so x comma 2 is a point on the parabola y squared is equal to 2x. So now I can just plug in 2 for y and find out what x is. So we get 2 squared is equal to 2x. You cancel that out, and that gives you x is equal to 2. So I guess it's just 2, 2, or did I do something wrong? Yeah, so 2, 2 is the closest point, and this is a point on the parabola. You may notice that in this book there are other examples, and they're more applied than this. But they're kind of dumb because they make assumptions that aren't really justified. So I didn't bother going over them. So for example, there's let me pull it up. There's example 2. I didn't bother going over this because there's this assumption. So you have, I mean, maybe I'm just being too knuckleheaded at the moment. My brain's too foggy and I can't see it. But it's kind of dumb because you have this problem and it says you have to make a cylinder. Yeah, I'm not even gonna bother going through it, but it's dumb. It's a dumb problem. If you can go work through it and make sense of it, you can, and that's just more practice, but you don't have to worry about example 2 and say example 4. There shouldn't be anything like that on the exam or the final. If there is something like that on the final, it's not by my choice because I don't make the final. But if there is a problem like that on the final, I will, like example 2 or example 4, I will definitely prepare you for that though. So don't worry. So we're going to look at one more example, and this is example 5. So first I need to, let me see. So let me write down example 5, and then I'll copy the figure over. So we want to find the area of the largest rectangle that can be inscribed in a semicircle of radius r. So the first step is to get the figure, draw a figure. In this case, I'm just going to copy. Oops. In this case, I'm just going to copy the figure because I don't want to have to draw all of this because it's not very easy to draw with this tablet. All right, so this is the setup. We have this rectangle in red, and we have this these inscribed means that these 2 vertices right here, you have this vertex here and then this vertex here, are points on the circle, and the circle is, we're going to just assume it's centered at the origin. So the corresponding equation for this is x squared plus y squared equals r squared. And of course, y has to be some greater than or equal to 0 because we're talking about the upper half. And so this point right here, if xy is on this side of the circle, then this point must necessarily be negative xy. And so we can describe the area then. So the area of this, we're going to call this the area of this rectangle A of xy, because it's a function. Technically, it's a function of x and y. It's going to be 2x. So it's the base. So the base is 2x because you have this distance right here is x, and then this distance right here is x. So that's how you get the 2x times y. So that's the height right here. That's the height y. But we know that So this is how you describe the area of the inscribed rectangle, but x comma y is a point on the semicircle oops. So it satisfies the equation x squared plus y squared is equal to r squared. So we can solve for x then, or sorry, y. So you just subtract x squared from both sides and you take the square root, but we're only going to take the positive square root because we're only going to consider the positive square root because y has to be a positive number. And so we can eliminate y. So what we end up with is y is equal to r squared minus x squared. And then that implies that the area can just now be written as a function of x. So it'll be 2x times y, but y is given by the square root of r squared minus x squared. And so what we want to do is we want to maximize this function. Oops. We're going to find a value of x for which this is has a maximum. So we need to take the derivative. So if we take the derivative, we have to use, so we have a product of two functions of x, 2x times square root of rx minus x squared. Well, actually, we can just ignore the 2 and keep it on the outside. So we'll have 2 times something in parentheses. So it's got the product rule says you take the derivative of the first function, which is just x times the second function. So the derivative of x is just 1. So the first term is just going to be square root of r squared minus x squared. And then you add in the first function times the derivative of the second function, and that's going to require the chain rule. So this right here is the same thing as r squared minus x squared, so 1/2. So we have this power, we have to use the chain rule with the power rule. We bring the 1/2 down. And then we multiply by the derivative of the inside function. So that's, well, the derivative of r squared, r is just some constant. So that will vanish. And then the derivative of negative x squared is negative 2x. And then times the derivative of the outside function, which is the square root function, evaluated at the inside function. So we already brought the power down. Now we just have to reduce it by 1 to get negative 1/2. Then we do that. At this point, so we have this 2 on the outside. We can try to simplify a little bit. So the negatives, the 1/2 and the 2 cancel, but then we have this negative here. And then we get x squared. And then this piece we'll just put in the denominator. So we get x squared over square root of r squared minus x squared. And then we need to get a common denominator, and the common denominator is square root of r squared minus x squared. So if we convert that, what we get is to a fraction, is what we get is r squared minus x squared divided by square root of r squared minus x squared over square root of r squared minus x squared. And then we can combine the two fractions and distribute the 2. Well, not really. But what we get is r squared, 2 times r squared minus negative 2x squared over the square root of r squared minus x squared. So actually, I should mention something up here at the top. The domain of this function is clearly this. X has to be between 0 and r. Now, so now what we need to do is find the critical number. So the critical number is wherever the function is not defined or where it is 0. So for its 0 is when the numerator is 0. So we have, let's say it's a 0 of a prime of x. That's 0 when the numerator is 0. And if you solve for that, you get, let's say 2x squared is equal to rx squared. And now you can divide by 2 and take the square root to get r. And we're going to take a positive square root because x is where x is supposed to represent this vertex right here. So x is positive. So just ignore the positive root. Or sorry, ignore the negative root. And then a point where let's look at where a of x, say undefined points of a prime of x. That's where the denominator is 0. So that happens when r squared minus x squared is 0, which implies that x is equal to r. So these two, so x is equal to r, and then r over square root of 2 are critical points. So this r is just the endpoint, right? R is endpoint of domain. So recall, the original function is given by this. And the domain of it is given by this. So in order to determine where the maximum occurs, we have to test the value of the function at the endpoints and the critical values, but one of the critical values is just the endpoint. But you can see that a of 0 is 0, and a of r is 0. So definitely not maximum. They're definitely not maximal values. And that kind of makes sense because let's think about what x equals r corresponds to. If x equals r, that means you slide this bead, like you can think of this vertex as a bead, and you slide it down all the way right here to this point. But now the rectangle you're looking at has no height. So the area is going to be 0. So that's obviously not going to correspond to maximal value. So now it's more than likely just going to be at that other critical point. So let's just see. So it should definitely be, if it's greater than 0, then we know it's the critical point. So we get 2 times r of root 2 over root 2 times r squared minus r over root 2 squared. And we get, let's see, let's simplify this. You get r squared over minus r squared over 2. And then you can, well, I guess you can combine it like fraction to get, but yeah, if you r squared minus r squared over 2 is just going to simplify to r squared over 2. So you multiply these two, well, let's just simplify it once more, times. So now square root of r squared over 2 becomes this. And then you get, you multiply the two fractions, you get r squared over 2, and then the 2's cancel. And you get r squared. which is definitely bigger than 0. So X, so what we can say is that the maximal area happens when X is equal to R over square root of 2. And then of course you can work out what Y is, because Y squared plus X squared is equal to R. So what is that? R squared. So that gives us Y squared plus we square X, which is R over square root of X, and that gives you R squared over 2. And then that's equal to R squared, and then you can simplify. So you subtract R squared over 2 from both sides, you get R squared over 2. And actually look at that, if you take the square root and take the positive root, you get R over root 2. So actually the X and Y coordinate have to be the same. So really what there is, so you're looking at this diagonal line. So the X and Y coordinate are the same. So you have the line Y is equal to X, and it intersects here at R over square root of 2, R over square root of 2. All right, so that's all. Maybe it depends. Maybe we'll go over another optimization example. I'll look at those other examples. Maybe they do make sense, and my brain is not working at the moment. And if they do, maybe we'll go over them, and then we'll finally we'll finish chapter 4 by going through 4.9, and then that will be all the material we need for our second exam.